All right, let's have a conversation about point estimates and interval estimates. The difference, why we need them, how to calculate them, and how to get all the missing pieces that we need. So first we'll start with a conversation about point estimations, and we're specifically focused on the population mean today. So an estimator is a strategy or rule that is used to estimate a population parameter. If the rule is applied to a specific set of data, the result is an estimate. Now, the point estimators that are used for a single point to estimate a population parameter. So because we're talking about estimations, we can leave out population parameters because those are not estimations. Those are exact values. We know what it is. We know the mean of the population, which means every single data value was used in order to calculate that. Same with P being the population proportion and sigma being the population standard deviation. They're not estimated. They are the exact value. But most of the time we do not have mu, P, or sigma when we are working with data. We have a sample mean, X bar. We have a sample proportion, P hat. We have a sample standard deviation, S, that we use in order to give our best guess of what's going on in the population. So for example, if I wanted to estimate the proportion of the US that voted for Trump or that voted for Biden, I could actually look that up. That is something that is obtainable on the internet. I can find the population proportion. Once the election actually finishes counting all the votes, I would be able to find it. But let's say that before the election happened, I wanted to get an idea, which happens all the time. They do exit polls around the country to give an idea of the way that they believe the voters are going to be voting. Let's say that I rounded up, randomly selected 1,000 likely voters and asked them who they were planning to vote for, and then I could come up with a P hat. That P hat is my best guess for the proportion of all voters who are going to vote for said candidate. So point estimation, we don't have any kinds of confidence about how close or accurate it is to the population parameter, but it's our best guess. An interval estimate defines an upper and lower boundary for an interval that will hopefully contain the population parameter. An estimation begins with a collection of data. A fundamental assumption for all statistical inference models is that the data for the inference is credible. Without credible data, any results from your inference are unsound. And we talk about this a lot. We say that it needs to be randomly selected. Okay, good sample collection methods, because if you do not collect your data in an unbiased, good way, then you can forget any of your calculations being valid or meaning anything. So one good thing about this interval estimate we're going to learn today is that the interval estimate does come with a level of confidence, and it also produces a margin of error that we expect there to be a difference between the sample mean and the population mean. So an estimator's average squared distance from the true parameter is referred to as the mean squared error, MSE. The mean squared error for the sample mean is given by the following formula. So we have the margin of error, which we're going to talk about what that formula looks like, times the difference between the sample and the population squared. Okay, we square it because when we're talking about margin of error, we want the positive version. And so squaring the difference ensures that we're working with positive values. And we'll talk about this margin of error in a bit. So as we previously discussed, to be an unbiased estimator, the estimated value of the estimator must be equal to the parameter that is being estimated. Among unbiased estimators of the population mean, the sample mean has the smallest mean squared error. Okay, now let's really get into that interval estimate, okay, with confidence levels. It's called a confidence interval as well. So an interval estimate is made by developing an upper and lower boundary for an interval that will hopefully contain the population parameter. At least that is our goal, is that this interval we're going to create will contain the actual population parameter. But this interval is not based on the population parameter. It is designed and created and calculated based off of the sample statistic. The term confidence interval is used to describe the method of construction rather than a particular interval. A 95% confidence interval can be interpreted to mean that if all possible samples of given size are taken from a population, 95% of those samples would produce intervals that capture the true population mean, and 5% would not. So if we were looking, for example, at a 90% confidence interval, let's say that we collected 10 samples of students and we calculated average GPA of those 10 samples. So there's 10 X bars. And in each one of those samples, we created a 90% confidence interval. What 90% confidence means is that out of those 10 samples and the confidence intervals that were calculated from them, we would expect 9 out of 10, which is 90%, 9 out of 10 of the samples to actually have the population mean included in the interval, while 1 of the 10 samples, the population mean would be somewhere else. So for example, let's say that the population average GPA for all students in a particular university is 3.5. Well, then we would see that 9 of the confidence intervals would contain 3.5 in those intervals, and 1 would have an interval that's either too small, so it stops before 3.5, or is too high, it starts above 3.5, leaving the actual population parameter out of the interval. Now, if sigma is known and the sample is drawn from a normal population, or our sample size is big enough, being bigger than 30, then we will use a z distribution. So this is the actual formula for a confidence interval, although we will be using Rguroo to calculate that. But unfortunately, Rguroo does not have everything that we need. So we will still need to resort to this formula in order to solve for things like the critical value. Z is our critical value. And sigma over the square root of n, we should be familiar with. That is our sampling error or our standard error for the mean. So that's something that's not new to us. Notice what's happening here. We have the sample mean, and we are adding this number after calculating it, and we're subtracting it. So that plus or minus is what's giving us our upper boundary. Subtract is our lower boundary. Okay, this formula here, z times the sigma over the square root of n, or z times the standard error, is what makes the margin of error. So this formula here, if we go back to that squared mean error, this is what's being multiplied on the other side. The right side of the plus or minus, this whole thing, is being multiplied by that difference of x bar minus mu squared. And we will work with this formula today, so no worries. Okay, the term z sub alpha divided by 2 represents the z value required to obtain an area of 1 minus alpha centered under the standard normal curve. That probably meant nothing to you, but that's okay, because we will do many examples to kind of make this make sense. The z values for obtaining various 1 minus alpha areas centered under the curve are given in a particular table in our book. And we can use this table to find critical values, or I will show you how to algebraically find the critical value. So here's a picture of what they're talking about. All confidence intervals, the confidence is in the center because we are confident that the population parameter is hopefully in this interval. And these purple areas on the outsides are the opposite of our confidence interval. It is the intervals that do not contain the actual population parameter. So you can see that they gave you 4 Z distributions. Okay, be very careful because we're going to introduce a new distribution today. For Z, all 80% confidence intervals, the critical value is 1.28. And for all 90% confidence intervals using a Z distribution, the critical value is 1.645. Be careful, Hawk's Learning usually likes you to round to 2 decimals, so you will have to round that to 1.65. 95% confidence interval, which is very popular, and the default if it's not mentioned, by the way. Hint, hint, keep that in mind. 95, 95, 95. You're going to see in Rguroo it defaults to 95 or the opposite of that, 0.05 all the time because it's the default. And the critical value for a Z distribution of a 95% confidence interval is 1.96. For 99%, we have 2.575. Again, Rguroo will most likely want you to round that to 2.58. Now, first example, a random sample of 100 car engines has a mean weight of 425 pounds. Construct the following confidence intervals for a population mean if the standard deviation of the population is 900. Okay, so we have to get comfortable now with checking whether we are going to use a Z distribution or whether we are going to use something that we're going to introduce, which is called a T distribution. So remember the criteria for the Z, let's go back. Criteria for Z is that we either know the standard deviation of the population or our sample size is bigger than 30. Okay, so standard deviation of the population is 900 and our sample size is bigger than 30, so we are good on both fronts, definitely using a Z distribution. So coming over here to Rguroo, we're going to go to Analytics, we're going to go to Analysis, we're going to go to Mean Inference, and as of right now, we're only working with one population. And for this course, we really are only going to work with one population. If you're interested about comparing 2 different populations, you should definitely take the advanced stats class because that's what we'll be doing. Okay, there's no data set, but that's okay. We will have an example where we have a data set, so we'll be able to practice with that. Right now, we're going to enter in our sample mean, which is 425 pounds. We don't know the sample standard deviation, but that's okay because we'd rather have the population one, which is 900. Our sample size is 100. Now, you do need to label the mean variable, or it will remind you and pop up a box and say, hey, you forgot to label mean. So this is mean weight. So we're going to say the mean of weight, and you can be more specific if you want, for car engines. All right, these probability plots or tests for normality are only applicable when you have a data set, so you don't need to select those or it will probably break down on you. We need to do all 4 of these. So first, let's do the 80%. So I'm going to change this to 80, and I'm going to select the Z because we've determined that we meet the criteria to use a Z distribution. I'm going to hit my eyeball. Okay, so I have my sample size, my mean, my population standard deviation. Here I can see for an 80% confidence interval, it's going to go between 309.66 and 540.34. So it's telling me that there is we are 80% confident that the population mean for the weight of car engines falls within 309.66 pounds and 540.34 pounds. Now the margin of error is 115 pounds plus or minus, which is quite a large margin of error if you think about it. We could be off by about 100 pounds plus or minus. Okay. I guess if car engines are really, really heavy, then that would be okay, but that's about a quarter of the mean. Sample mean is a margin of error. That seems really large. Probably not that accurate, but We're also only looking at 80% confidence. We should really take a look as we go through this, what happens to that confidence interval as we change the confidence level. So let's go ahead and do that. So let me make a note of what the answers are so we can take a look at these comparisons when we're done. So we have 80% gives us 309.66 to 540.34, and the margin of error being 115.34. Okay, let's now do the next one, which is 90. So if we just select this basic, then we don't have to worry about retyping in all this stuff. We just change this to a 90 and select the eyeball. So now this is changed, 90% confidence interval, and we have from 276.96 pounds to 573.04 pounds with a margin of error that just grew to almost 150 pounds plus or minus. Let's do the 95%. So now change this to 95. Again, nothing else is changing. Eyeball. For our 95% confidence interval, we now have a lower boundary of 248.6 pounds and an upper boundary of 601 pounds. Margin of error has increased to 176.4 pounds. Last one is the 99. Again, I'm just hitting the basic button. And I don't have to change any of this data. I just need to change the confidence level. And my 99 interval goes from 193.18 to 656.82 with a margin of error now increased to 231.82 pounds. That is about half. Right? That is even over half of the estimated sample mean or the point estimate. This 425 is your point estimate. So that's a huge margin of error. We are adding and subtracting 231 pounds on either side in order to be 99% confident that the population parameter, the overall average car engine mean weight is within this interval. So if we take a look at these intervals, let's take a look at what's happening. So I'm going to switch over to a whiteboard real quick. So for our 80%, we were looking at a confidence interval from 309.66 to an upper boundary of 540.3 pounds with a margin of error of 115.34. For our 90% confidence interval, we were looking at 276.96 with an upper limit of 573.04 with a margin of error of 148.04 pounds. Here we go. Our 95% confidence interval ran from 248.6 to an upper level of 601.4 pounds. The margin of error increased to 176.4, and our 99% confidence interval goes from 193.18 to 656.82 with an increased margin of error of 231.82 pounds. Now, let's talk. The margin of error formula is this critical value that is dependent on we'll put ZC, this is the confidence level. Now we chose that over here. These are the confidence levels, okay? And it's this critical value times the standard error. So since our standard deviation for the population stayed at 900 and our sample size n stayed at 100, the standard error had no effect. It did not change from 80% confidence level to 99% confidence level. The only thing that was changing was the confidence level, which affects this critical value. And if we look back at the PowerPoint, which I'll bring us back there in a moment, actually, let's go back now. Hold on. So if we take a look back at this layout of critical values, as the confidence level gets more and more confident, what we're seeing is that the critical value is got to be bigger. Okay, so we're multiplying by a bigger number, which increases the margin of error. We're adding and subtracting, therefore, a larger number on either side of the point estimate x bar sample mean. And that's why the intervals have to get bigger for us to be more confident. Now, that kind of makes sense, right? So if we want to be 99% confident versus 80% confident, we're going to have to widen the interval in order to feel more confident that the population parameter fits inside that interval. So I've left some slides in here for you that includes the work done out in case you were interested in seeing how these numbers came about if we were to do it out by hand, which some of this work today we are going to have to do out by hand, so it's good to see the formulas. Now, maximum error and margin of error, which we were just talking about, is the formula to the right of the plus or minus. The part of the expression that is added and subtracted to the point estimate, like I just said, the critical value times the standard error, can be thought of as the maximum error in estimating the population parameter mu using the point estimate x bar, sample mean, with a specified level of confidence. The maximum error of estimation is also referred to, as I call it most likely, most of the time, the margin of error, and denoted by big capital E. Next example, we have an analyst that is interested in investigating the average durability of the bladder within the soccer balls that his company manufactures. Suppose a random sample of 100 soccer balls is selected and the balls are put through a pressure test to determine the PSI, which is pressure per square inch, at which the bladder will burst. It is known from past experiences that the population standard deviation of the pressure at which a ball bursts is 13.2 psi. The sample mean psi necessary to pop a soccer ball is found to be 147.58 psi. Let's calculate a 95% confidence interval for the population mean pressure per square inch necessary to pop a soccer ball. Okay, before we can even move on to Rguroo, we need to check whether we are using a Z distribution or soon introduced T distribution. So remember the requirements is we look at the sample size. Oh, it's bigger than 30. We're good to go with a Z. And we also have the population standard deviation, sigma, which also means use a Z. So we're going to come over here, we'll start fresh, go over to analytics, analysis, mean inference, one population. Type in the sample mean that's given. They give us a sample mean of 147.58. Our population standard deviation is 13.25. And our sample size is 100. The label of the mean, we are talking about mean PSI. So I'm just going to put PSI there. And we do want to calculate the defaulted 95% using a Z distribution. Okay, again, I've told several students the best way to remember how to use Rguroo is to pause the video at this point and take a picture of what I've entered in from the PowerPoint. PowerPoints are set examples that you can use to make sure you're doing the other examples correctly. So here we go for a 95% confidence interval. We have ourselves 144.98 psi to 150.18 psi. Our margin of error is only about 2.5 pressure per square inch units. And so we are 95% confident that the population parameter for PSI to pop a soccer ball falls within these upper and lower limits. Let's introduce the t-distribution now. So this is a new distribution. The z, remember, was the standard normal curve where we knew the mean was always 0 and the standard deviation was always 1. If the population, however, has a sample drawn and it's normally distributed, or our sample size is big enough, but the population standard deviation is not given, okay, but the population standard deviation is unknown. Really important. If the population standard deviation is known, then you always use a z. But if we do not know this population standard deviation, and I should put in parentheses because students always see a standard deviation and assume we know sigma, not true. We only know the sample standard deviation. So we're always going to know a standard deviation. Depends on whether it was calculated from the population or whether it was calculated from just a sample. Okay, if it was just calculated from a sample, well, they're known as S, then we're going to use what's called a student's t-distribution. Okay, so this is the t-score, as we would call it. And S is the standard deviation of the sample. So we're not using sigma because we don't know sigma. Now here, typically we use the t-distribution when it's specifically stated that it's normally distributed and n is less than 30. Okay, because if n is greater than 30, then we qualify to use that z distribution, which is probably better to use because it is standardized. But this t-distribution, let me give you a little insight on why this t-distribution needs to be used when we have unreliable sample sizes. Again, really only works if you have a normally distributed population, and we don't have the very accurate population standard deviation. We only have the inaccurate from a small sample size sample standard deviation. So, some properties of this t-distribution. The mean, the median, and the mode are all equal to 0, so that's the same as the z. The mean will always be centered at 0. It's symmetric. It's bell-shaped. The total area under the curve is 1, just like the z distribution, because we're talking about probabilities. At some point, we're going to be using the t, and we need the area to be equal to 1. The differences, well, the tails of these t-distributions are thicker than those of the z distribution, okay, because we have to account for more inaccurate data, so that means that more of the error is stuffed into the curve. More of the area is in the tails, leaving the center with less area, and that's, again, to balance out and help with the fact that we're working with a really small sample size. Standard deviation of the t-distribution is not regulated at 1. In fact, it varies depending directly on what the sample size is that we're working with. Now, that dependency is called the degrees of freedom. We calculate degrees of freedom by taking the sample size and subtracting 1. And I will explain a little bit about the degrees of freedom in a moment. Let me give you a picture first. So, picture the standard normal curve, this blue line, as Big Brother. Okay, so that's the z distribution. The blue curve is the z distribution, and the black and gray are the t depending on the degrees of freedom. So you can see as the degrees of freedom get bigger and bigger, we get closer and closer to the z distribution. So I think of the z distribution as Big Brother and the t distributions as the little siblings that are looking up to Big Brother saying, I'm going to be you one day. And as our sample size gets larger, we get closer to the z. So at approximately bigger than 30, really it's closer to 100, but around 30, our critical values start coming out to be about the same, and therefore we can switch from using these these curves with big fat tails to the standard normal once our sample size gets big enough. Now, the t-distribution has one parameter, and that is again called the degrees of freedom. The number of degrees of freedom is a number of values from the sample that can vary after imposing restrictions on the data. So for example, given the specific value for the mean of a set of data with n equals 5, so think about it. Think about asking a survey question to just a sample size of 5 people. I hope you guys can agree that that doesn't sound very accurate, which is why we have to use the t-distribution to balance that inaccuracy. But anyway, so we are looking at a sample size of 5, then 4 of the data values can vary freely, whereas the 5th one would be determined, meaning it would have to have a particular value in order for the 5 data values to have the specified mean. Therefore, the number of degrees of freedom is always equal to the sample size minus 1. Now, if sigma is unknown and the sample size is drawn from a normal population, again, this should really emphasize and n is less than 30, because other than that, we're really going to be working with a z-distribution. Then we are looking at the same formula. The only thing's different is instead of a z critical value, we have ourselves a t. And we, instead of sigma, the population standard deviation, we have s, the sample standard deviation. Okay, we have our confidence interval and our margin of error. Same setups for the formulas, just different pieces that got fit in because of what we're given or not given. For example, we're getting through this. A random sample of hours worked in a week by student interns is drawn from a normal population. We need to get very excited when we read this and pay attention to the fact that this is important. This means that our calculations will be valid no matter the sample size. Okay. So we have a normal population with unknown mean and variance. The 7 data values sampled are as following. We need to construct a 95% confidence interval for the population mean hours worked in a week by students. Okay, well, this one has a data set, so it's a very small one. You could technically probably calculate the mean on your own, but the standard deviation would be a little tricky. So let's just create a data set. So we're going to data import, create new data set. I'm going to name my variable name is going to be hours. And you know what I'm going to put in? There are 7 of them. So let me just put my rows in so I can just type them. Okay, so we have 25, 19, 37, 29, 40, 28, 31. Again, don't forget after you create a data set to save the data set. So I'm going to come over here and save it. No idea why this is. Not showing you everything. Let's do that. Okay, so you would name this and click save. I've already done that. It's right here, our 10.2 example for a T confidence interval. Don't forget to double click in order to make sure that it was imported properly or created properly. All right, so I'm going to delete that one because I already saved this. Okay, so here's our data set. In order for us to, if we wanted to pull the mean, the sample mean and sample standard deviation, remember we can calculate sample statistics with it, but that's automatically going to be done once we put it into the confidence interval window. So we're going to go to Analytics, Analysis, Mean Inference, One Population. This time we're going to select a data set, and you have to select the variable. Now notice sample mean, sample standard deviation, and the count, the sample size is automatically calculated based on the values in the data set. And your mean is already going to be labeled based on what you labeled the variable. Now, I do need to run a normality plot and a test for normality. Well, actually, I don't, because it told me in the problem that the population is normally distributed, but I want to do it just in case we need to do it in the future, and I can't remember if there's a problem that has us do it. I'm pretty sure there is, but let's just double check, and I'll show you what to look on those tests. It wants a 95% confidence level, and we are, let's see, we have a small sample size less than 30, but it's valid because there's a normal population, and we do not have the population standard deviation given. Therefore, we definitely need a t-test statistic. All right, hitting our eyeball. So now, first thing I want to look for is my test for normality. So here's your test for normality and the conclusion. You don't even need to be able to read this right now. It tells you data are normally distributed. Okay, so, well, that's our null hypothesis. And here's our p-value. We will learn about p-values and hypothesis testing, which is coming up very shortly. But let's just say a really big p-value means yes, it's normally distributed. And this graph, you will be able to determine normal distribution if it is a linear distribution. So notice these dots are hovering along this linear line, and that graphically shows us that this does produce a this sample does come from a normally distributed population. Now, we really go into detail about the test of normality in advanced stats, but it's really good for you to at least take at the graph, because again, you do really need to understand p-values to interpret the test. But the graph itself, as long as the dots are in a linear line, you're good to go. If they create like a quadratic, a parabola looking thing, or they look like a spray can, sprayed them everywhere, then that would tell us that we are not pulling samples from a normally distributed population. So our confidence interval is from 23.3 hours to 36.4 with a margin of error of 6.5 hours. So we are 95% confident that the population parameter of mean hours worked in a week by student interns specifically falls within 23 to 36 hours. Okay, so in here we see that they also plotted the normality plot to show that it's approximately normal. And here is the critical value that was used in order to calculate this confidence interval that we came up with. Okay, so this matches, thank goodness. And here's our conclusion. Okay. An alternate interpretation would be that we are 95% confident that the point estimate, 29.86 hours, and we get that from here, here's the mean, has a maximum error of estimation or margin of error of 6.5 hours, which we got from this value here. Next example, a manufacturing company is interested in the amount of time it takes to complete a certain stage of the production process. The project manager randomly samples 10 products as they come from the production line and notes the time of completion. The average completion time is 23.45 minutes with a sample standard deviation of 4.32 minutes. Based on this sample, construct a 95% confidence interval for the average completion time for that stage in the production process. Let's assume that the population distribution of completion times is approximately normal. So here we have approximately normal. We have a really small sample size, and we are only given the sample standard deviation. So with all of these pieces, we can conclude we need a t-distribution in order to solve this problem. So I'm going to come over here to my analytics, my analysis, my mean inference one population screen. I don't have a data set for this, but I have a sample mean of 23.45, a sampled standard deviation of 4.32. Recall, if this said variance, Remember, the one step you'd have to do to get standard deviation is to take the square root of variance. So keep that in mind. That happens a lot in our problems we work in. Our sample size is 10. Our label is going to be minutes. Okay, so this is mean of minutes. It's the amount of time it takes to complete a certain stage in a production problem. So let's just go with minutes. We want 95% confident. We've decided a t distribution is best. So we see here that we have our 95% confidence, our point estimate, the sample mean, our standard error, which is that sigma over the square root of n, or in our case, because we're working with a sample standard deviation, it's s over the square root of n. So this number was calculated by taking 10, which is our sample size, but really taking sample standard deviation of 4.32 and dividing it by the square root of 10, which is what gave us 1.3661. That's going to be helpful when you need to find a critical value, which we'll do next. Degrees of freedom, remember, is sample size minus 1, so 10 minus 1 gave us 9. And we are 95% confident that the population average time to complete a certain stage of the production process falls within 20 minutes to 26 minutes with a margin of error of 3 minutes, which is a really tight margin of error if you think about it. So we're within 3 minutes plus or minus. Now, a lot of the questions you're going to be working on are going to require you to first find the critical value, that t critical value. And I suggest working backwards. So do your confidence interval first. And then you can use these values. Specifically, we can use the standard error and the margin of error values, knowing the formula, in order to calculate the critical value. So you can use the table. If you look at the help in the Hawks Learning homework, it does tell you to use this table appendix, which is perfectly fine to use. But if you want to stick with this technology and not necessarily go to tables, well, we know that the margin of error is equal to the test statistic, or rather the critical value t, times the standard error. Oh, wait. That's got to be an S. Okay, so since we know that the standard error is 1.3661, and since we know the entire margin of error is 3.0903, we can solve very easily for our critical value. So if we solve for this, we just have to divide by the 1.3661. So if we take 3.0903 and divide by the standard error of 1.3661, that is going to give us our critical value. So if I put that in my calculator, because Hawks Learning again is asking me for that, I type in 3.0903 divided by 1.3661, and I would say my critical value t is equal to 2.26. And this is plus or minus because it could be either one. It really doesn't matter. Honestly, you should just keep the positive one, and hopefully the homework stick with that they don't ask you to for both. Not that it matters, it's the same number. Okay, so that's how you could find that critical value. Very simple, by using the numbers that Rguroo has already produced for you. It's a simple division. So very easy step there. Get rid of that. Okay, again, I've left these in the PowerPoint for you to kind of take a look at how the formula was produced. And there you go. There's that critical value, 2.26, which we calculated. Thus, we are 95% confident that the true average completion time of that stage of the process is between the lower and upper limit we've calculated. There's a flow chart that I think would be very helpful when determining where to go, whether to use a t distribution or normal z distribution. So if your population is normally distributed or you have a larger sample size, you're going to move on to, well, is the population standard deviation known? If it's not, use the t. If it is, then use the z. Okay, if not, then we cannot use the parametric methods that we know of, and we would have to rely on non-parametric methods, which we do not cover in this course. That is an advanced stats topic. Last thing in this section is talking about minimum sample sizes. So let's say that we are our friend is running for student government, and we're curious about how many students would I have to sample to get an accurate reading on who will vote for my candidate. Let's say we want to be within a certain margin of error, plus or minus 2 students or something like that. And we want to be 95% confident. Well, we would use this formula in order to determine what our minimum sample size is in order to get our desired results. So for example, let's consider a population having a standard deviation of 15. We want to estimate the mean of the population. How large of a sample is needed to construct a 95% confidence interval for the mean of this population if the margin of error is equal to 1.5. Okay, so we just have to place the items into this formula based on what we know. Now, the only problem we're going to have is finding this critical value for these problems. But remember, you were given the basic ones, and these examples don't use t, they only use z. And there is a chart for that. So if you look in your appendix of your book, there is a table for critical values. But you're really going to end up using a lot of the same ones that were given in this PowerPoint. So 95%, if we go back to that slide, way up here, 95% produces a critical value of 1.96. Go back down. So we have 1.96, which is directly correlated to the 95%. And let me show you where this comes from in the table. So if I Google standard normal table, okay, and really just go to the images, and I select, you really should do from the book. Some of these are different, so I strongly recommend you use the book's version of this table. But let me see, that's this one. Okay, let's see if we can get it bigger. I really should have went to the book and got the actual Z table. Here we go, this one works though. So what we're looking for is 95% confident. Usually has a little cheat sheet table at the bottom for critical values. Ooh, Z-score calculator, that's fun. Unfortunately, we don't have the population mean, so that's not going to help us. Okay, so I'm going to have to show you guys how to find that critical value, just in case it's one of the 95% is really common, but if we get uncommon ones, I want to make sure you guys know how to get that critical value. And honestly, a table is so old school, so I am going to resort to something else instead. Let's go to classcalc.com, which is a free calculator. Yes, this can be done in your TI calculator as well using inverse norm. You can look that up if you're more interested in that. We need to explore the calculator, and this would be under the graphing calculator. So this is classcalc.com, and you could just explore the graphing calculator, come down here and select stats. Now, you're probably going to have to replay this video a couple times to remember these steps because we don't use class calc very often, but this is the quickest way to find that critical value. And you can use this for both. Maybe you can't use it for the t. I don't see the t, inverse t showing up here. So if we use inverse CDF, which is the inverse z, and I click on this little explanation, okay, maybe not. Usually it tells me what I'm supposed to put in here. Let's say, should just be able to put in the area in the left tail. So if 95% is in the middle, then that leaves us with 2.5% in each of the left and the upper tail. So that's 0.025. I feel like it needs something else. Where's the help button on this thing? I used to use this all the time, and now I feel as though I forgot where the help button is. There used to be a help button that told me what to put in there. Okay, example. No, that's not what I wanted to do. That's something different. Okay. Probably should have practiced with this before we did this video. Okay, not a big deal. So I will post a video on how to do it in the TI calculator, and I know I've done it in class calc before, but it's slipping my mind on how to get that critical value from class calc. But you can do it in the TI calculator, or you can do it in that table. One thing you're going to need to know if you're using the table, or even if you're using the calculator, you do need to know the area in the left tail. So let me give you a visual of what you need to know in order to do these calculations. So let me clear. Oh, I can't do that now because I'm writing. So we have a standard normal curve. Remember, the confidence intervals are always in the center. So let's say they want us to do random 85% confident. And we're trying to find these Z critical values that bound the confidence area. All right. So the critical values are these positive and negative Z's that bound the middle confidence level. And when you're trying to find this value, the calculator is going to want the area in this left tail. So in order to get that, you take the total area in the curve, which is 1, subtract what you know is not in that tail, leaving us with 15% total. But that 15% is for the area in both tails. So if you want the area in just one tail, because we know these curves are symmetric, we divide by 2. And so 0.15, I didn't do a very even number here, 0.15 divided by 2 is giving us the area of 0.7.5% in each tail. So we would be saying that the area is 0.075 in the left tail, which would allow us to calculate the critical value. So let me, you know what? I just want to make sure you guys have the steps. So instead of posting a separate video, let me just walk you through how you would do this in your calculator. And then I will go back to that table that I already deleted and show you how to find the critical value in the table, because I want to make sure you guys know how to get this critical value. Wish I remembered how to do it in class calc, because that would have been way easier. All right. Let me again, here in the table, you can see they need the left area. Since we know the left area is 0.075, If you're using the table, you are looking in here for 0.075 or as close as you can get. So here's 0.035, 0.07, what was it, 75 is what I'm looking for. Okay, so we can see that this value right here, oh, I can't highlight it. This value right here, 0.0749 is the closest to 0.075. And we see that the critical value is negative 1.44, negative 1.44. Now, if you were doing this in a calculator, then let me show you, let me write out what the steps would be because I can't show a calculator on the screen. So our steps would be that in your calculator, you would want to go to second vars, which above vars says distribution. So second vars, find the button that says vars. You'll see above it, it says distribution in the same color as the second key. You'll get to a menu, a distribution menu. So keep it on the first menu. You'll see distribution and you'll see draw. Ignore the draw menu and stick with distribution. And scroll down to option 3, the inverse norm. Okay, so we select inverse norm. If you have an older calculator, it's going to bring you to the home screen where it's just going to kind of be blinking there like, hey, fill me in. You need to know that this is area to the left, which is what I just showed you with the picture of how to calculate the area to the left. And then you need the mean and the standard deviation, which we know that this is calculating Z standard scores, which are always 0 and 1. So we don't have to question that. Our area to the left for this problem is 0.075. And then we hit enter. So for a specific example, you should see in your home screen, let me erase this out of here. 0.075, 0, 1. And we see that the Z-score is negative 1.439, blah, 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 which rounds to negative 1.44 as we already seen with the distribution table. Okay, so that's 2 different ways. If you have a TI calculator, you can use this, follow these steps to get the critical value, which you need for this formula. Use the positive version, use the other side of the curve. So don't use the negative. That just is asking for you to make another mistake or a potential mistake in your calculations. Or you can use the table by finding the area in the left tail and then finding it in the center of the table, like we showed here. 0.07 rounds to 5, negative 1.44. All right, so coming back to this problem, that's how the 1.96 was found, because we took the 95% and calculated the area in the left tail, which would be 0.025. If we look in here for 0.025, here it's exactly 0.025, negative 1.96. And again, you can use the positive version. The 15 is the standard deviation, sigma. Okay, that was said here. And the 1.5 was stated to be the margin of error. Remember, that's denoted by big E. And if you stick this in your calculator, we can see what it comes out to. There is a calculator in Rguroo that I learned about. So if we come over here to applets and calculators, it's using Desmos. So if I come over here and I calculate with the scientific calculator, you do have to double click it, weirdly enough, even though everything else you don't have to double click. And if I want to calculate this right in Rguroo, I have parentheses, 1.96 times 15 divided by, oops, we're going to need another set of parentheses. So times 15. This is divided by 1.5. Then we are going to need another set of parentheses around this so that we can raise it to the square, to the second power. So we need to, oh, that's not, where is the exponent key? Oh, here we go. Raise it to the second power. And we see that it's 384.16. Now, rule of thumb for minimum sample sizes is that you have to always round up. Why? Because we're talking about a minimum. So if you need 0.16 of a person to make this happen, that means you need a whole nother person. So 385 is that minimum sample size. Whew. Okay, so rounding up, we have to have a sample size of 385 to ensure that we get at least a 95% confidence interval with a margin of error equal to 1.5. Next example, suppose that a quality control manager at Argon Chemical Company wishes to measure the average amount of cleaning fluid the company is placing in their 12-ounce bottles. From previous studies, they believe their population standard deviation to be 0.3 ounces. How large a sample must be taken in order to be 95% confident of estimating the mean cleaning fluid in a 12-ounce bottle to be within 0.05 pounds? Now, within is your key word. That 0.05 is the margin of error, which is not always that obvious. Now, our critical value is the same as the last example, 1.96. The standard scores never change, although the t critical values change all the time depending on the sample size, so be careful there. So if we stuff this into the formula, we get 1.96 times the standard deviation of 0.3 divided by the margin of error, which was defined by the words within, and we get 138.3, which again, we're going to round up to 139 as our minimum sample size for this problem. Being able to know the accuracy of your estimate is one of the significant benefits of inferential statistics. In this case, if 139 bottles are measured, we will be 95% confident that the resulting sample within 5/100ths of an ounce, 0.05, of a true mean. That's close. Another example, an airline's maintenance manager desires to estimate the average time in hours required to replace a jet engine in a Boeing 767. How large a sample? How large a sample? Keywords that tell you to use that N equals formula. Would be necessary if the manager wishes to be 95% confident. Again, critical value is 1.96. Of estimating the mean within. Anything following that word is going to be your margin of error, so 0.25, quarter of an hour. Assume the preliminary sample size is 31, has an average replacement time of 16.7 hours with a standard deviation of 4.3. So since we're only doing minimum sample size, that sample mean and standard deviation was extra information that was not needed in order to calculate this specific calculation. We take the 1.96, which was the critical value for 95%, and we multiply it by the standard deviation of 4.3. Okay, we did need the standard deviation. We just didn't need the mean. And we divide by the margin of error of 0.25 and square it, giving us 1,136.5. Rounding up, 1,137 is our minimum sample size in order to make that criteria they wanted to happen. So for example, suppose the sample standard deviation after sampling the first 100 observations was 4.1. Using this estimate of S instead of 4.3 results in a sample size of 1,034 compared to the original specification of 1,137. The notation of modifying the sample size estimate as additional data is observed can be applied at regular intervals during the sampling process until the estimate of the standard deviation stabilizes. So what they're saying is if you do not have the population standard deviation, it is okay to use the sample standard deviation in this formula, but you need to know that it is less accurate. And therefore, replication is called for in order to try to get that sample standard deviation as close to the population one as possible. Because we see here we are short by 103 people, which will throw off our numbers as we continue on through our calculations. All right, this ends our discussion of point and interval estimators.